What if the dream of reaching the stars was never actually possible? Not because of money, not because of politics, not because we lack the technology or the will or the courage, but because of something so simple, so brutally obvious that it hides in plain sight, right there in the arithmetic, waiting for someone ruthless enough to actually look at it. Richard Feynman was that kind of person. And I don't mean that the way people usually mean it when they call someone a genius. I mean it in a way that genuinely unsettled the people around him. Because Feynman didn't just think differently. He had this almost predatory instinct for finding the one thing in any problem that nobody wanted to say out loud. The single fact that made everything else irrelevant. The load-bearing wall hidden underneath years of jargon, politics, an institutional pride. He could walk into a room full of the most decorated scientists on the planet and within minutes, locate the thing they had all been unconsciously avoiding. Then he'd point at it, and the whole illusion would collapse. We saw it happen live, on national television, during the investigation of the Challenger disaster. NASA had assembled the greatest engineering minds in the country. Weeks of closed-door hearings, thousands of pages of reports, press conferences, political pressure, an entire machinery of complexity designed, or whether intentionally or not, to obscure a single devastating truth. Feynman sat down at the table, picked up a rubber O-ring, dropped it into a glass of ice water and waited. The rubber went stiff. That was it. That was the whole mystery. A billion-dollar space program, 7 lives, a national tragedy, and at the center of it was a simple fact about what cold temperatures do to rubber. The kind of thing a mechanic would know, hidden in plain sight, buried under everything else, now. What happens when you take that same ruthless strip-everything-away way of thinking, and you aim it directly at humanity's greatest ambition, the dream of becoming a spacefaring civilization? What Feynman's lens reveals about rocketry is not the kind of thing you'll see in a SpaceX launch video. It won't appear in a TED Talk. It doesn't make a good bumper sticker. It is quiet, it is mathematical, and it is, depending on how you look at it, either the most terrifying or the most fascinating thing you will ever learn about the future of our species. We are not talking about engineering challenges, but we are not talking about funding or politics or rocket materials. We are talking about arithmetic. Numbers so simple a child could check them. Numbers that have been sitting there since the dawn of the space age, perfectly visible, hiding in the open. And once you see what those numbers actually say, you will never look at a rocket launch the same way again. Before we go there, tell me where you're watching this from right now. Are you in bed staring at the ceiling with your headphones in? On a train with the world smearing past the window? Standing in a kitchen doing something forgettable while your brain quietly craved something worth thinking about? Drop it in the comments. I read them. Everyone matters to me, and it helps me understand who I'm really making this for. If this is the kind of journey you live for, hit like. So subscribe and come with me. Get comfortable, because what comes next is going to rearrange something in your head. And it starts with the simplest math you have ever seen. Here is the setup. You're floating in empty space. There's nothing around you for millions of miles. You want to move. There's no road beneath you, no air around you, no water to push against, no current to ride, no wind to catch. The only way to accelerate is to throw something in the opposite direction. Newton's third law. Every action demands an equal and opposite reaction. You brought a bag of rocks. Throw one behind you and you drift forward. Throw another, you speed up a bit more. Simple enough. Now here's where the trap closes. Those rocks you're throwing have mass. You had to carry them with you from the very beginning. Every rock you plan to throw later is dead weight you have to accelerate right now. The faster you want to go, the more rocks you need to throw. The more rocks you carry, the heavier you are at the start, which means you need even more rocks to get the whole collection moving, which makes you heavier still, which demands more rocks, which makes you heavier again. This is not a linear problem, it's exponential. Each additional unit of speed demands a disproportionately larger amount of fuel. The mathematics do not creep upward. They explode. They do not climb a staircase. They climb a wall that leans further over you with every step. The formal description of this relationship is called the Tsiolkovsky rocket equation, named after the Russian schoolteacher and visionary Konstantin Tsiolkovsky, who first derived it in 1897. Working in almost complete isolation in a small town in rural Russia, Tsiolkovsky captured the central dilemma of spaceflight in a single elegant formula, decades before anyone built a rocket capable of reaching the upper atmosphere. The equation states that the change in velocity a rocket can achieve depends on two things: the speed at which it expels its exhaust, and the natural logarithm of the ratio between its fully fueled mass and its empty mass. Written in words, it says this: to double your speed, you do not double your fuel. You must multiply your fuel by a factor that grows exponentially. If reaching a certain speed requires a fuel-to-payload ratio of 10 to 1, reaching twice that speed does not require 20 to 1. It requires something closer to 100 to 1, 3 times the speed, closer to 1,000 to 1. The numbers climb with terrifying steepness. The curve bends upward like a wall, and no amount of engineering genius can flatten it. The mathematics are absolute. Feynman understood this implicitly because he thought about physics in terms of energy budgets. He often asked what a process costs, not in dollars, but in joules. Where does the energy come from? Where does it go? How much gets wasted along the way? This accounting mentality cut through rhetoric and forced every claim about physical processes to justify itself in hard numbers. And when you apply energy accounting to rocketry, the ledger is devastating. Consider the Saturn V, the rocket that carried astronauts to the moon during the Apollo program. It remains one of the most powerful machines ever built by human hands. Standing 363 feet tall on the launch pad at Kennedy Space Center, it towered over everything around it like a cathedral built for leaving the planet. Fully loaded, it weighed approximately 6.5 million pounds. The payload it delivered to lunar orbit weighed roughly 100,000 pounds. That means for every pound of useful hardware that reached the moon, 65 pounds of rocket stood on the pad in Florida. But even that ratio understates the problem. Most of those 6.5 million pounds were fuel. The first stage alone, powered by 5 enormous F1 engines generating 7.5 million pounds of thrust, burned through roughly 4.5 million pounds of kerosene and liquid oxygen in just 2.5 minutes. 2.5 minutes. And in 150 seconds, the Saturn V consumed more fuel than a commercial airliner burns crossing the Atlantic Ocean 500 times. And what did that monstrous expenditure accomplish? It lifted the vehicle to an altitude of roughly 42 miles and accelerated it to about 6,000 miles per hour. Impressive by everyday standards, and extraordinary even if you were standing on the Florida coast watching the sky split open with fire. But orbital velocity around Earth is approximately 17,500 miles per hour. The first stage, consuming roughly 70% of the rocket's total fuel, got the vehicle to only about 1/3 of orbital speed. 70% of the fuel for 1/3 of the velocity. That is the exponential trap announcing itself. And the second stage burned another 1 million pounds of liquid hydrogen and liquid oxygen to push the remaining hardware close to orbital velocity. The third stage provided the final kick to reach orbit, and later reignited to send the spacecraft toward the moon. By the time the crew reached lunar orbit, more than 99% of the original vehicle had been discarded, jettisoned in pieces that tumbled back toward Earth, or drifted silently through cislunar space. The command module that splashed down in the Pacific Ocean weighed about 12,000 pounds out of 6.5 million. Less than 0.2% of the original vehicle survived the journey. Feynman would have looked at those numbers and seen the unmistakable signature of exponential scaling. Not a failure of engineering, but a confession of physics. The rocket equation does not care about your engineering. It does not care about your budget, your ambition, your deadline, or the speeches your politicians make about national prestige. It imposes a tax on every kilogram you want to move, and that tax compounds mercilessly. Here is another way to feel the weight of this constraint. The energy stored in rocket fuel is measured by a quantity called specific energy, the amount of energy released per kilogram of propellant. For the best chemical fuels available, liquid hydrogen burned with liquid oxygen, the specific energy is approximately 13.5 megajoules per kilogram. That sounds like a lot. It is enough to power a typical household for several hours, but escaping Earth's gravitational field requires approximately 63 megajoules for every kilogram of payload. So that means even with perfect efficiency, no energy lost anywhere, every joule converted cleanly into upward motion. You would need at least 4.5 kilograms of the best chemical fuel for every kilogram you want to lift into orbit, and perfect efficiency is impossible. Real rockets lose energy to atmospheric drag, to gravity pulling the vehicle downward during the agonizingly slow first seconds of ascent, to heat dissipation in the engine walls, and to structural mass that does not contribute to propulsion. Actual mass ratios for reaching low Earth orbit typically range from 15 to 1 up to 20 to 1. 15 to 20 kilograms of vehicle and fuel for every kilogram of payload delivered. This is where Feynman's thinking becomes particularly sharp. And he would recognize immediately, though, that the gap between theoretical and practical efficiency is not the real problem. The real problem is that chemical energy itself is fundamentally limited. It has a ceiling, and we are already pressing our fingers against it. Chemical bonds store energy in the electromagnetic interactions between atoms. When hydrogen burns with oxygen, electrons rearrange themselves into lower energy configurations, releasing the difference as heat. This is the energy that propels rockets. It is the same basic process that powers candles, campfires, and internal combustion engines. But electromagnetic interactions operate at energy scales measured in electron volts per atom. A few electron volts here, a few there. Compare this to nuclear reactions, and which operate at energy scales measured in millions of electron volts per atom. Chemical energy is roughly 1,000,000 times weaker than nuclear energy. Atom for atom, 1,000,000 times. This is not a fact about current technology. It is not a shortcoming of modern chemistry or a problem waiting for a clever graduate student to solve. It is a fact about the structure of matter itself. No chemical fuel, no matter how cleverly designed, no matter what exotic combinations of elements you experiment with, can exceed the energy density set by the strength of electromagnetic forces. Liquid hydrogen and liquid oxygen already represent one of the most energetic chemical reactions known to science. We are not leaving performance on the table. We are pushing against a ceiling set by the laws of quantum mechanics. The ceiling is hard, and it is low. Feynman spent much of his career working at the boundary between quantum mechanics and electrodynamics. He understood better than almost anyone alive at the time that the electromagnetic force has a fixed strength, characterized by the fine structure constant, a pure number approximately equal to 1 over 137. This constant determines how tightly atoms hold their electrons, which determines how much energy chemical reactions can release, which determines how fast a chemical rocket can expel its exhaust. The fine structure constant is not adjustable. It is not a design parameter. It is woven into the deepest fabric of physics. Every chemical rocket ever launched has operated within the narrow energy band permitted by this constant. The Saturn V, the Space Shuttle, the Atlas, the Delta, the Falcon 9, the Starship, all of them burn chemicals, all of them are subject to the same exponential penalty dictated by the same exhaust equation. All of them discard most of their mass as fuel during ascent. The engineering has improved enormously since the 1960s. Engines are more efficient, materials are lighter, computer guidance systems are incomparably smarter, manufacturing is more precise and less wasteful, but the fundamental ratio between fuel and payload has not changed dramatically, because it cannot change dramatically within the constraints of chemical propulsion. The fine structure constant has not budged. The ceiling has not moved. This realization strips away the optimistic veneer that often surrounds popular discussions of space travel. Science fiction and breathless news headlines present rocketry as an engineering challenge, a problem of building bigger, better, smarter machines. Give the engineers enough funding and enough time, and they will crack it. Feynman's thinking reveals it as something deeper, not an engineering challenge, but a physical constraint built into the universe at the most fundamental level. A constraint that cannot be solved, only endured. Consider what the exponential nature of the rocket equation means in practice. Suppose you want to send a 1 kilogram payload to orbit using chemical rockets. You need approximately 15 to 20 kilograms of fuel and structure to deliver it. Expensive, but manageable. Now suppose you want to send that same payload to the moon. Then the additional velocity change required means you need a larger fuel fraction, which means a larger vehicle, which means more fuel to carry the larger vehicle. The compounding continues. The exponential function does its ruthless arithmetic. By the time you calculate the requirements for a Mars mission, with enough supplies for a crew to survive the journey, descend to the surface, conduct operations, and return to Earth, the numbers become staggering. Hundreds of tons of fuel for each ton of useful cargo. And every kilogram of that fuel must itself be lifted off the launch pad at a cost of 15 to 20 additional kilograms per kilogram. Now scale the problem to the outer solar system. A mission to Jupiter requires velocity changes so large that the mass ratios become absurd, numbers that would make an accountant weep. So without gravity assists, which cleverly steal momentum from planets, Chemical rockets simply cannot reach the outer planets with useful payloads in reasonable timeframes. The Voyager probes, which carry only a few hundred kilograms of instruments each, required Saturn V class launch vehicles and carefully choreographed planetary flybys to reach the outer solar system. And they carry no fuel for deceleration. They are on one-way trajectories flying through the outer solar system at speeds too high to ever stop. They will coast forever, their instruments slowly dying, their radio signals fading to whispers. Because the exponential trap made it impossible to carry enough fuel to slow down. This is the exponential trap. It does not gradually increase the difficulty of space travel the way a hill gradually steepens. And it savagely multiplies it with every additional kilometre per second of velocity you demand. Each step up the velocity ladder costs more than the last. And the cost does not grow by addition. It grows by multiplication, then multiplication of the multiplication, then multiplication of that. Feynman once described physics as the study of nature's rules, the underlying principles that determine what is possible and what is forbidden. He was not interested in what engineers could build within some temporary budget constraint. He was interested in what the universe allowed, what the laws of nature permitted, and what they did not. And when it comes to moving mass through space using chemical energy, the universe allows very little. It permits a narrow window of performance bounded above by the fine structure constant, and bounded below by the cold realities of structural engineering. Within that window we have done remarkable things, but the window is small and no amount of brilliance can widen it. The most efficient chemical rocket engine ever built, the Space Shuttle main engine running on liquid hydrogen and liquid oxygen, achieved a specific impulse of approximately 453 seconds in vacuum. Specific impulse measures how long 1 kilogram of fuel can produce 1 newton of thrust. Higher is better. 453 seconds represents the practical ceiling for chemical propulsion. It is not a record waiting to be broken, it is a boundary waiting to be acknowledged. No chemical reaction can significantly exceed this number, and because no chemical bond stores significantly more energy than the hydrogen-oxygen reaction. 453 seconds sounds abstract. So here is what it means in terms a physicist like Feynman would appreciate. It corresponds to an exhaust velocity of roughly 4.5 kilometers per second. To reach low Earth orbit requires a velocity change of approximately 9.5 kilometers per second when you account for gravity and drag losses during ascent. The rocket equation says the mass ratio needed is e raised to the power of 9.5 divided by 4.5. That works out to approximately 8:1, meaning 88% of your launch mass must be fuel. For every kilogram of payload and structure reaching orbit, roughly 7 kilograms of fuel burn away during ascent. And not because the engine is wasteful, because exponential mathematics demands it. Now consider what it would take to build a single-stage vehicle that reaches orbit without discarding any hardware along the way. You would need a structural mass fraction below 12%, meaning the empty vehicle, engines, tanks, avionics, game heat shield, landing gear, everything must weigh less than 12% of the fully fueled vehicle. The remaining 88% is pure propellant. No material currently known to science can achieve this structural fraction, while also surviving the stresses of launch, the vibrations of supersonic flight, the heat of atmospheric re-entry, and the impact of landing. This is why every orbital rocket in history has used staging, discarding empty tanks and engines to shed dead weight during ascent. Not because engineers lack creativity, but because single-stage performance with chemical fuels is physically beyond reach. Staging is brilliant engineering. It works around the exponential penalty by starting fresh with a smaller, lighter vehicle partway through the ascent. When the first stage runs dry, you throw it away. The upper stage ignites with a much more favourable mass ratio, because it does not have to carry the weight of the empty first stage. It is an elegant trick, like paying off a compound interest debt in installments rather than letting it accumulate. But staging does not eliminate the penalty. Each stage still obeys the rocket equation individually. Staging simply distributes the exponential tax across multiple smaller payments, rather than one impossible lump sum. Feynman would have appreciated the elegance of staging as a mathematical workaround, the kind of clever solution that operates within a constraint rather than pretending the constraint does not exist. He would also have recognized its limitations. You cannot stage infinitely. Each stage adds complexity, weight, failure points, and cost. Practical rockets use 2 to 3 stages. The diminishing returns kick in quickly. Beyond 3 stages, the added complexity, the additional structural mass, the extra separation mechanisms, and the increased risk of failure often cancel out the theoretical benefits. The trick works once, twice, maybe 3 times, then the universe calls the bluff. The exponential trap is not a challenge to be overcome, it is a fact to be lived with. Every mission designer, every rocket engineer, every astronaut who has ever strapped into a capsule and listened to the countdown clock tick towards 0 has negotiated with this constraint. They have found clever workarounds, ingenious compromises, and bold trade-offs. They have pushed structural mass fractions lower, engine efficiencies higher, and mission profiles closer to theoretical optima, but they have never escaped the fundamental exponential scaling that makes space travel so punishingly expensive in terms of energy, mass, and cost. They cannot escape it. No one can. It is not a wall to climb over. It is the ground beneath your feet. This is Feynman's insight distilled to its essence. Space is hard, not because we lack imagination or resources or willpower. Space is hard because the physics of self-propelled motion in a vacuum imposes an exponential tax on every gram you want to move, and exponential functions are merciless. They do not negotiate. They do not bend to clever engineering. They do not care about inspiration or ambition or national pride. They simply grow and grow and grow until the numbers overwhelm everything you brought to the table. The next question becomes obvious. If the fuel penalty is this severe just moving through empty space, what happens when you add gravity to the equation? Earth is a prison, not a metaphorical prison, not a philosophical prison, not some poetic abstraction used to make a point about the human condition. A gravitational prison, a physical cage with walls made of curved space-time and a depth measured in megajoules per kilogram. The walls are invisible, but they are absolute. You cannot see them, cannot touch them, cannot negotiate with them. But try to leave and you will feel them resist every gram of mass you attempt to lift. Before any spacecraft can begin its journey through the cosmos, before it can visit another world or photograph a distant asteroid, or carry a human being toward another planet, it must first pay the toll of escaping the gravitational well that holds everything on this planet's surface firmly, unyieldingly, stubbornly in place. And that toll is far steeper than most people realize. The concept of a gravity well provides one of the most useful ways to understand why leaving Earth is so fantastically expensive. Imagine space-time as a rubber sheet stretched tight across an enormous frame. The sheet is flat and featureless in the absence of mass. Now place a heavy ball on the sheet. It creates a depression. The heavier the ball, the deeper the dip. Objects near the ball roll toward it, trapped in the curved surface drawn inward by the geometry of the sheet itself. To escape, they must climb up and out of the depression, fighting the curvature every centimetre of the way. And climbing requires energy. The deeper the well, the more energy you must spend. This is not a perfect analogy. The real physics involves 4-dimensional space-time curvature described by Einstein's field equations, and gravity wells extend in all 3 spatial dimensions, not just downward into a flat sheet. But the core insight holds. Mass curves space-time. Curved space-time traps objects. Escaping that curvature costs energy, always. Without exception. Earth's gravity well has a specific measurable depth. The energy needed to move 1 kilogram from Earth's surface to infinity, completely free of Earth's gravitational influence, never to fall back, is approximately 63 megajoules. This quantity is not negotiable. It is not approximate in any meaningful sense. It is determined entirely by Earth's mass and radius. 2 numbers that nature fixed billions of years ago when this planet coalesced from the debris of the early solar system. No engineering innovation can reduce it. No future technology can lower the price. No brilliant breakthrough waiting in some laboratory will ever change this number. If you want to leave, you must pay exactly this amount, plus whatever inefficiencies and losses accumulate along the way. 63 megajoules per kilogram may not sound catastrophic in isolation. It is a number. It sits there on the page looking manageable. A kilogram of gasoline contains roughly 46 megajoules of chemical energy. So in theory, a bit more than a kilogram of gasoline could provide the energy needed to lift 1 kilogram to space. 1.5 kilograms of fuel to liberate 1 kilogram of payload. That sounds almost reasonable. You might read that and think, well, space travel should be only modestly harder than driving a car across a continent. But this naive calculation ignores everything that makes rocketry brutal in practice. It ignores the very thing we spent all that time establishing. First, the fuel itself has mass. Every kilogram of fuel you carry must also be lifted, which requires additional fuel, which has additional mass, which requires still more fuel. The exponential compounding we explored in Part 1 does not politely step aside when gravity enters the picture. It gets worse. The gravitational cost and the rocket equation's exponential penalty multiply together, creating a combined tax that neither constraint would impose alone. They are partners in a conspiracy against spaceflight. Second, you cannot simply convert chemical energy into gravitational potential energy with perfect efficiency. Rocket engines convert thermal energy into directed kinetic energy of exhaust gases, and that conversion involves thermodynamic losses that no engine design can fully eliminate. Heat escapes through engine walls. Exhaust gases carry away energy in random thermal motion that contributes nothing to thrust. The nozzle expansion is never perfectly matched to ambient pressure. These losses are built into the physics of heat engines, governed by the same thermodynamic principles that Feynman lectured about with such devastating clarity at Caltech. Third, and this is where Earth's gravity well becomes truly punishing, Earth has an atmosphere. The atmosphere adds a penalty that does not appear in the clean mathematics of the rocket equation, but devastates real missions in ways that are difficult to overstate. During ascent, a rocket must push through air. Not thin air, not wispy traces of gas. Dense, heavy, resistant air that fights back harder the faster you move through it. The drag force grows with the square of velocity, meaning that doubling your speed does not double the atmospheric resistance. It quadruples it. Triple your speed, and drag increases by a factor of 9. At the velocities needed for orbital insertion, atmospheric drag becomes a physical wall of compressed air that the rocket must batter through while simultaneously fighting gravity and accelerating towards 17,500 miles per hour. The velocity penalty imposed by atmospheric drag amounts to roughly 1.5 kilometers per second. That number sounds modest until you remember what we established about the rocket equation. Every additional kilometer per second of required velocity demands exponentially more fuel. 1.5 kilometers per second of drag loss translates to hundreds of tons of additional propellant for a large launch vehicle. Hundreds of tons of fuel that exists solely to push through air. Fuel that would not be needed if Earth had no atmosphere. The fuel whose mass must itself be carried and accelerated, compounding the exponential penalty further. But drag is only one component of atmospheric losses. There is also gravity loss, a penalty that arises from the simple maddening fact that gravity pulls the rocket downward during the entire ascent. Every second the engines fire, gravity is working against them. While the vehicle climbs, gravity continuously decelerates it, stealing momentum that the engines must replace with additional thrust. The longer the ascent takes, the more energy gravity steals. A rocket that hovered in place, engines roaring, burning fuel without climbing, would eventually run dry without gaining a single meter of altitude. All of its energy would go into fighting gravity, with nothing left over for actual motion. In this extreme case, it illustrates why ascent profiles are designed to minimize time spent in the gravity well. Get high, get fast, get out. Every second of delay costs fuel. For a typical orbital launch, gravity losses add another 1 to 1.5 kilometers per second to the required velocity budget. Combined with atmospheric drag, steering losses, and the gap between theoretical orbital velocity and the real velocity budget, the numbers become grim. Add these penalties together. The theoretical velocity needed for low Earth orbit is approximately 7.8 kilometers per second. This is the speed at which an object, if magically placed at orbital altitude with no atmosphere to contend with, would circle Earth indefinitely. Gravity losses during ascent add roughly 1.5 kilometers per second. An atmospheric drag adds another 1.5. Steering losses, which arise from the rocket not flying a perfectly optimal trajectory, because trajectories must account for safety corridors, range limits, and abort options, add a few hundred meters per second more. The total velocity budget for reaching orbit from Earth's surface climbs to approximately 9.5 kilometers per second, 20% more than the theoretical minimum. 20% sounds manageable until you feed it back into the exponential function. That extra 20% does not cost 20% more fuel. Because of exponential compounding, it costs far more. The additional velocity budget cascades through the rocket equation, inflating mass ratios, demanding larger tanks, heavier structures, more powerful engines, all of which add mass, and all of which demand still more fuel. the 20% penalty becomes a 50% increase in launch mass, or worse, depending on the specific vehicle and mission profile. Feynman thought about problems like this in terms of energy flows. He was relentless about tracking where energy came from and where it went. Energy enters the system as chemical potential energy stored in fuel, neatly packed into molecular bonds waiting to be broken. It exits the system in multiple forms. Kinetic energy of exhaust gases streaming backward at thousands of meters per second. Kinetic energy of the vehicle climbing upward. Heat lost to the atmosphere through drag. Heat radiated from engine bells and nozzle walls. Gravitational potential energy gained during ascent. Sound energy shaking the ground for miles around the launch pad. Then the fraction that ends up as useful payload energy in orbit, the only output that matters, is shockingly small. For a typical expendable rocket, the overall energy efficiency from chemical fuel to payload delivered to orbit is roughly 1 to 2%. 98% of the chemical energy released during launch goes somewhere other than the payload. It heats the atmosphere. It accelerates exhaust gases that will never be used again. It lifts structural mass that gets discarded. It fights drag. It fights gravity. It fights everything, 1 to 2%. Imagine a car that converted only 1 to 2% of its gasoline into forward motion, wasting the rest as noise and heat. You would never drive it. You would call it Buchan. But for rockets launching from the bottom of Earth's gravity well through a thick atmosphere, that 1 to 2% is not broken. It is the best physics allows with chemical fuels. This appalling efficiency is not a failure of engineering. Rocket engineers are among the most talented and meticulous professionals in any field. They have spent decades optimizing every component, shaving grams, refining combustion cycles, perfecting nozzle geometries. The low efficiency is a consequence of the exponential mass penalty, thermodynamic limits on engine cycles, atmospheric drag, and gravity losses all compounding together simultaneously. Even a theoretically perfect rocket engine, a magical device with zero heat loss and perfect thermodynamic conversion, burning the most energetic chemical fuel known, would achieve overall efficiencies of only a few percent when launching from Earth's surface. The physics sets the ceiling. Its engineers work beneath it. Now consider what this means for specific impulse, the standard measure of rocket engine efficiency that separates capable engines from merely adequate ones. Specific impulse represents how many seconds 1 kilogram of fuel can produce 1 newton of thrust. For chemical rockets, the range runs from approximately 260 seconds for solid fuel boosters, the kind strapped to the sides of the space shuttle, to approximately 453 seconds for the best liquid hydrogen engines ever tested. That is the entire range, the full span of chemical propulsion performance available to humanity. 260 to 453, a band so narrow it barely qualifies as a range at all. The reason this band is so confined goes back to physics that Feynman understood at the deepest level. Specific impulse is directly proportional to exhaust velocity, which depends on the energy released per kilogram of propellant and the molecular weight of the exhaust products. Lighter exhaust molecules move faster for the same energy input. This is simple kinetic theory. Give a bowling ball and a tennis ball the same energy, and the tennis ball moves faster. This is why hydrogen-oxygen engines outperform kerosene-oxygen engines, despite kerosene being denser, cheaper, and easier to handle. Hydrogen combustion produces water vapor. Molecular weight 18. Kerosene combustion produces a mix of water vapor and carbon dioxide with a higher average molecular weight. Lighter exhaust, faster exhaust, higher specific impulse. But there is a ceiling, and we are already pressing against it. The maximum exhaust velocity for any chemical reaction is limited by the bond energies of the reactants and the molecular weight of the products. The hydrogen-oxygen reaction releases approximately 15.9 megajoules per kilogram of water produced. This energy becomes thermal motion of the exhaust molecules. The lighter the molecules, the faster they move. And water molecules are already among the lightest possible combustion products for any reaction that releases comparable energy. You cannot find a chemical combination that simultaneously produces lighter exhaust and releases more energy. Chemistry does not allow it. The periodic table has been thoroughly explored. The ceiling is real. It is low compared to what ambitious space travel demands. And it cannot be raised by any advance in chemistry or material science. This is why rocket scientists obsess over mass fractions with an intensity that borders on religious devotion. If you cannot improve the energy per kilogram of fuel, The only remaining lever is reducing the mass of everything that is not fuel. Propellant tanks must be thinner, shaved down until they barely contain the pressures inside them. Structural members must be lighter, optimized through computational analysis that would have been impossible a generation ago. Engines must be designed to maximize thrust while minimizing weight, a balance so delicate that single-digit percentage improvements represent years of engineering effort. The pursuit of lighter structures has driven some of the most impressive materials engineering in human history. Modern rocket tanks are milled from single blocks of aluminum-lithium alloy to eliminate the weight of welds and fasteners. Carbon fiber composites wrap around pressurized tanks to carry structural loads that would otherwise demand heavier metals. Three-dimensional printing creates engine components with internal cooling channels, so complex they would be impossible to machine conventionally. Friction stir welding joins panels without the heat-affected zones that weaken traditional welds. These advances are real and meaningful. Each one represents genuine ingenuity applied to a genuine problem, but they are fighting on the margins of an exponential function, clawing back percentage points against a tax that grows by factors. Consider the impact of reusable rockets, and arguably the most significant development in spaceflight economics in the past 2 decades. When a first stage lands on a drone ship in the Atlantic Ocean and flies again months later. Instead of being discarded on the ocean floor, the economic cost of reaching orbit drops substantially. The hardware investment, the engines and avionics and tank structures that cost tens of millions of dollars, is amortized across multiple flights instead of being written off after a single use lasting 8 minutes. This represents a genuine revolution in the business of space access. It has opened low Earth orbit to commercial ventures that would have been economically impossible a decade ago. But reusability does not change the physics. A reusable first stage must carry landing fuel, typically 5 to 10% of its total propellant load, reserved for the deceleration burns and landing maneuver. It must carry landing legs heavy enough to support the empty stage on a pitching deck. It must carry grid fins for atmospheric steering during descent. It must have reinforced structures to survive the thermal and mechanical stresses of re-entry and landing, stresses that expendable stages never face. This additional mass, every kilogram of it, reduces the payload the rocket can deliver to orbit on each flight. The fuel consumed during ascent remains identical, the velocity budget remains identical, the exponential mass ratio remains identical. Reusability makes space access cheaper in dollars. It does not make space access cheaper in joules. The gravity tax remains unchanged. The bill is the same, only the payment plan has improved. To appreciate how severe Earth's gravity well truly is, step back and compare it to other bodies in the solar system. This comparison reveals not just the difficulty of our situation, but the profound cosmic irony embedded in it. The Moon's escape velocity is approximately 2.4 kilometers per second compared to Earth's 11.2. This means the energy needed to escape the Moon's gravity is roughly 1/20th of Earth's gravitational penalty. 1/20th. A rocket launching from the lunar surface would need dramatically less fuel per kilogram of payload, dramatically less structure, dramatically less everything. And the Moon has no atmosphere whatsoever. No drag losses, no heating, no need to balance ascent speed against aerodynamic pressure. A lower gravity means smaller gravity losses during the shorter ascent. A vehicle launching from the Moon faces a fundamentally different energy landscape than one launching from Earth. The same physics, the same equations, but with numbers so different, they produce an entirely different practical reality. Mars sits between the two extremes. Its escape velocity is approximately 5 kilometers per second, less than half of Earth's. Its atmosphere, though present, is less than 1% the density of Earth's at sea level. Thin enough to impose minimal drag during ascent, but remarkably thick enough to allow aerobraking. Aerobraking uses atmospheric friction to slow an arriving spacecraft rather than burning precious fuel for deceleration. Mars offers this dual advantage: easy to leave, at least compared to Earth, and cheaper to arrive at than a body with no atmosphere at all. This combination makes Mars significantly more accessible than Earth as a launch platform for deeper space missions, a fact that drives the logic behind proposals to manufacture fuel on the Martian surface using local resources. The smallest bodies in the solar system illustrate Earth's gravitational severity by contrast so extreme it borders on comedy. The escape velocity from the asteroid Bennu, a rubble pile roughly 500 meters across that the OSIRIS-REx mission visited and sampled, is approximately 20 centimeters per second. 20 centimeters per second. A human being could achieve escape velocity from Bennu by jumping. Not jumping hard, just jumping. A leisurely push off the surface would launch you into solar orbit, never to return. The energy needed to leave Bennu is so trivially small that the concept of a gravity well barely applies. There is no well. There is a shallow dimple, a minor inconvenience that any source of energy, no matter how feeble, can overcome. Even Ceres, the largest object in the asteroid belt and massive enough to have pulled itself into a roughly spherical shape, has an escape velocity of only about 510 meters per second. A cannon could launch cargo off Ceres. The energy costs of leaving these small bodies are negligible compared to the crushing penalty Earth imposes. This comparison reveals something profound and somewhat cruel about humanity's cosmic situation. We evolved on one of the most gravitationally demanding launch pads in the inner solar system. Only Venus, with its similar mass and crushing atmosphere, would be harder to launch from. We developed intelligence, curiosity, and the ambition to explore the cosmos on a planet whose gravity well is deep enough to require the most powerful machines ever built just to reach the near-space environment a few hundred kilometers overhead. Our planet's mass gives us a breathable atmosphere, thick enough to block lethal ultraviolet radiation and distribute heat across the surface. It gives us a protective magnetic field generated by convection currents in a molten iron core, heavy enough to stay liquid for billions of years. It gives us a stable climate moderated by oceans held in liquid form by atmospheric pressure and surface temperature. These features make Earth habitable. They are the reason complex life exists here at all. They are the reason we are alive to contemplate leaving. They also make Earth extraordinarily difficult to leave. The irony is precise, almost surgical. The same gravitational strength that holds an atmosphere capable of supporting life also imposes an enormous energy penalty on any attempt to escape that life-giving embrace. A planet light enough to escape easily would lack the gravity to retain a substantial atmosphere. Its surface would be bathed in unfiltered radiation, baked dry, bombarded by micrometeorites with nothing to slow them. A planet heavy enough to sustain complex life, to develop oceans and weather and breathable air, traps that life beneath a gravitational wall that demands exponential fuel expenditure to overcome. Feynman would have recognized this as a fundamental trade-off, the kind of unavoidable physical compromise that permeates nature at every scale. Yet you cannot have a habitable surface and an easy exit. The universe does not offer both. The physics is non-negotiable. You get one or the other. And Earth, by the accidents of its formation 4.5 billion years ago, chose habitability. We are the beneficiaries of that choice, and its prisoners simultaneously. This gravitational trade-off shapes every aspect of space mission design in ways that cascade from the grandest strategic decisions down to the smallest engineering details. The mass of every single component must be justified against the fuel cost of carrying it through the gravity well. Every kilogram added to a spacecraft in orbit required roughly 15 to 20 kilograms of fuel on the launch pad below. A 1 kilogram camera added to a satellite demands 15 kilograms of rocket fuel. And a 100 kilogram astronaut suited and supplied demands 1.5 metric tons of fuel. A 10,000 kilogram habitat module demands 150 metric tons. These are not estimates. They are consequences of the rocket equation operating within Earth-specific gravitational parameters. These ratios explain why space hardware carries price tags that look like misprints. Every component must be engineered to extreme precision and minimum mass. Every bolt, every wire, every bracket, every connector represents grams that cost hundreds of dollars per gram to launch. The aerospace industry does not charge exorbitant prices because of corporate greed or institutional inefficiency, though critics sometimes assume so. It charges those prices because the physics demands that every gram of mass be scrutinized, analyzed, tested, qualified, and minimized before it earns its place on a launch vehicle. The gravity tax creates an economic multiplier that inflates the cost of every object that leaves the planet. An ordinary laptop computer costs $1,000. A space-rated laptop designed to survive launch vibrations and operate in vacuum, while weighing as little as physically possible, costs 50 times that. Not because the circuits are different, but because the grams are precious. This is why the International Space Station, weighing approximately 420 metric tons in orbit, required over a decade of construction and more than 40 separate assembly flights to build. It is why proposed lunar bases are designed around minimal mass and maximum reuse of every component. And it is why Mars mission architectures almost universally call for manufacturing return fuel on the Martian surface, extracting carbon dioxide from the thin atmosphere and hydrogen from subsurface ice, rather than carrying round-trip propellant from Earth. Carrying enough fuel from Earth's surface for a Mars round trip would require launch masses so enormous that the mission collapses under its own weight before it begins. Every mission planner on Earth fights the same implacable enemy, the gravitational penalty of launching mass from the bottom of Earth's deep, deep well. The atmospheric component of this penalty deserves one final note, because it eliminates alternatives that would otherwise seem promising. Earth's atmosphere extends roughly 100 kilometers above the surface. At a thin shell compared to the planet's radius of 6,371 kilometers, if Earth were the size of a classroom globe, the atmosphere would be thinner than a coat of varnish. Yet this vanishingly thin shell imposes disproportionate costs on any attempt to reach space. The densest portion of the atmosphere, where drag is most severe, occupies only the first 10 to 20 kilometers of altitude. A rocket must punch through this region at relatively low velocity to avoid catastrophic aerodynamic heating and structural failure, then accelerate aggressively once drag diminishes in the thinner air above. The optimal ascent profile balances these competing pressures with extraordinary precision, minimizing total energy losses while keeping structural stresses within survivable limits and thermal loads below material failure thresholds. The atmosphere also prevents certain launch techniques that would otherwise be enormously attractive. Electromagnetic launch systems, sometimes called mass drivers or railguns, can accelerate payloads to orbital velocity along ground-based tracks. The technology works, the physics is proven. But any object reaching orbital speed at sea level, 7.8 km per second through dense air, would be instantly and catastrophically destroyed. The compressed air ahead of it would reach temperatures exceeding 10,000 degrees, hot enough to vaporize any known material. The object would not fly to orbit. It would become a brief, brilliant fireball a few meters from the end of the launch track. The same atmosphere that sustains human life makes surface-based orbital acceleration physically impossible, forcing us back to the slow and expensive fuel-intensive approach of carrying engines and propellant through the atmosphere and burning them above it. This atmospheric barrier means that all Earth-launched vehicles must gain most of their velocity above the dense lower atmosphere, which means carrying fuel and engines through that atmosphere as dead weight during the early phase of ascent, burning them only after climbing above the worst of the drag, which adds mass, which requires more fuel, which adds more mass. The exponential trap from Part 1 feeds on itself here, with gravity and atmosphere acting as willing accomplices, each penalty compounding the others in a cascade that multiplies the cost of every mission beyond what any single factor would impose alone. Feynman's insight applies here with uncomfortable, almost cruel clarity. The difficulty of leaving Earth is not primarily an engineering problem awaiting a sufficiently clever solution. It is a physics problem rooted in constants that were fixed when the universe established the strength of gravity and the masses of atoms. The gravitational depth of our planet and the density of our atmosphere set hard constraints that no rocket design can circumvent. Engineering can approach these limits more closely, extracting a few more percentage points of efficiency, shaving a few more grams from structures, optimizing a few more seconds of specific impulse. It cannot move the limits themselves. The walls of the prison do not care how sophisticated your tools are. The question that follows naturally is whether these constraints relax once you escape Earth's gravity well and enter the vacuum of interplanetary space. The answer is both encouraging and deeply discouraging, depending entirely on where you want to go and how quickly you need to get there. Reaching orbit is only the first step. It feels like a triumph, and it is. Escaping Earth's gravity well is the single most energy-intensive maneuver in any space mission. The brutal uphill climb that consumes 90% of your fuel before you have travelled even a fraction of a percent of the distance to your destination. But once a spacecraft clears that well and settles into the quiet vacuum of low Earth orbit, coasting at 17,500 miles per hour with its engines finally silent, a new reality sets in. And that reality is in many ways more daunting than the launch. The distances between destinations in space are so vast, and the energy required to traverse them so enormous, that even the most ambitious propulsion concepts humanity has ever conceived struggle to cope. The solar system, which looks compact and orderly in textbook diagrams, is in truth a cathedral of emptiness, with a few specks of matter scattered across incomprehensible gulfs. Getting from one speck to another is not merely difficult. It is an exercise in negotiating with the same exponential mathematics that made the launch so expensive, but now applied across distances that make the 100-kilometer climb to orbit look like stepping off a curb. The first surprise for anyone studying orbital mechanics is that space travel does not work the way intuition suggests. And every instinct built into the human brain by millions of years of navigating terrestrial landscapes becomes not just useless but actively misleading. On Earth, if you want to reach a distant city, you point your vehicle toward it and drive. The path curves only because roads follow terrain. The fundamental logic is simple. Face your destination, apply force, arrive. In space, this logic will kill you. Or more precisely, it will strand you in an orbit that goes nowhere near your target while consuming all your fuel in the process. You cannot point your spacecraft at Mars and fire the engines. In a gravity-dominated environment, trajectories follow curved paths determined by orbital dynamics. The ceaseless gravitational choreography between the Sun, the planets, and any object moving among them. And every spacecraft in the solar system is at every moment falling toward the Sun, falling toward a planet, falling along a curved path dictated by its velocity and the gravitational field it inhabits. Changing your destination means changing the shape of that fall. Not overriding it, you do not fly to Mars. You reshape your orbit until it intersects with the orbit Mars happens to occupy at a specific future moment. Getting from Earth to Mars requires not a straight line, but a precisely calculated elliptical transfer orbit that touches Earth's orbit at one point and Mars's orbit at another. The spacecraft does not travel from Earth to Mars. It travels from one orbit to another, swinging outward along an ellipse that the Sun's gravity defines. And because both Earth and Mars are themselves moving along their own orbits at different speeds, the geometry must be calculated with extraordinary precision. Missing the timing by even a few days can add months or years to the journey, or make arrival impossible entirely without burning fuel that was never budgeted. The standard method for travelling between planets is called a Hohmann transfer orbit, named after the German engineer Walter Hohmann, who described it in 1925 in a publication that was largely ignored at the time because the spaceflight was considered science fiction. Hohmann was a city architect by profession, not an aerospace engineer. He worked out the mathematics of interplanetary travel as an intellectual exercise decades before anyone had the technology to attempt it. His calculations turned out to be exact. A Hohmann transfer uses 2 engine burns and only 2. The first burn occurs at Earth. It accelerates the spacecraft by a specific amount, just enough to stretch its orbit into an ellipse, whose farthest point reaches Mars's orbital distance from the Sun. The spacecraft then coasts for months along this ellipse, engines completely off, consuming no fuel at all. It is falling around the Sun along a path that mathematics guarantees will intersect Mars's orbit at a predetermined point in space and time. When it arrives near Mars, a second burn slows the spacecraft enough to be captured into orbit around the red planet. 2 burns, months of coasting, everything between is free, paid for by the initial investment of velocity. This technique is extraordinarily fuel efficient, and it requires the minimum possible energy to move between 2 circular orbits. Hohmann proved this mathematically. No other 2-burn trajectory can do it cheaper. But this efficiency comes at a price that reveals another of nature's non-negotiable trade-offs. It is also extraordinarily slow. A Hohmann transfer from Earth to Mars takes approximately 8 to 9 months, depending on the relative positions of the 2 planets at departure. 8 to 9 months of drifting through the vacuum in a small metal container, far from any possibility of rescue or resupply. And the timing windows are narrow, almost cruelly so, because Earth and Mars orbit the Sun at different speeds, Earth completing a full orbit every 365 days and Mars requiring 687. The geometry for a minimum energy transfer aligns only once every 26 months. Miss the window and you wait more than 2 years for the next opportunity, not because of engineering delays or budget shortfalls, but because the planets are in the wrong positions, and no amount of fuel can make an efficient trajectory from the wrong geometry. The Hohmann transfer illustrates a fundamental trade-off in orbital mechanics that Feynman would have identified immediately as another manifestation of nature's absolute refusal to offer something for nothing. Speed versus fuel. A faster trajectory to Mars is certainly possible. You can burn more fuel at departure, entering a higher energy transfer orbit that reaches Mars in 4 months instead of 8. But burn more fuel and you trigger the exponential trap, that every additional kilometre per second of departure velocity demands exponentially more propellant mass, subject to the full compounding of the rocket equation. And that additional propellant must itself be launched from Earth's surface, multiplied again by the 15:1 mass ratio of the gravity well. A slower trajectory conserves fuel but extends mission duration, which brings its own cascade of penalties. Humans need to eat. They need to breathe. They need water, radiation shielding, medical supplies, and exercise equipment to prevent bone and muscle deterioration in microgravity. Every additional month of transit adds mass to the life support systems, which adds mass to the vehicle, which adds fuel to the launch, which adds mass to the launch vehicle. For crewed missions, that the choice between speed and efficiency becomes a choice between two different exponential penalties, one measured in propellant and the other measured in consumables. Neither is free, both compound. There is no escape from this trade-off. It is inherent in the physics of orbital motion. You can have speed or you can have efficiency, but you cannot have both. And the rocket equation punishes any attempt to choose speed with exponential ferocity. The velocity change required for a Hohmann transfer from Earth to Mars is approximately 3.6 kilometers per second for departure and roughly 2.1 kilometers per second for arrival, depending on the specific transfer opportunity. These numbers seem modest compared to the 9.5 kilometers per second needed to reach Earth orbit in the first place. Yet you might look at them and think the hard part is already over. But remember the compounding. Every kilogram of fuel for the Mars departure burn must first be launched into Earth orbit. That kilogram of Mars fuel required 15 to 20 kilograms of launch fuel to reach orbit. And the Mars fuel itself has mass that the departure burn must accelerate, which demands more Mars fuel, which demands more launch fuel. The layers stack. The exponential function compounds through each layer. For a crewed Mars mission carrying enough supplies for a crew of 6 during an 8-month transit, a surface stay of weeks or months, and a return trip home, the total mass required in low Earth orbit has been estimated at between 500 and 1,000 metric tons, depending on mission architecture. At current launch costs, so delivering that mass to orbit would require dozens of heavy-lift launches over a period of months or years, assembly of components in orbit, and a total expenditure measured in tens of billions of dollars. The engineering is feasible. Nothing about a Mars mission violates known physics. The economics are staggering. And the physics, the same exponential scaling that makes every kilogram precious, is the reason the economics are so brutal. Beyond Mars, the numbers become far worse. The solar system is not arranged for human convenience. Jupiter orbits the Sun at an average distance of approximately 5.2 astronomical units, compared to Mars's 1.5. 1 astronomical unit is the distance from the Earth to the Sun, roughly 93 million miles. Jupiter is nearly 4 times farther from the Sun than Mars, and a Hohmann transfer to Jupiter takes roughly 2 years and 9 months of coasting through empty space. The velocity change required is larger, the transit time is longer, and the fuel requirements multiply with the same merciless exponential scaling that governs every other aspect of rocketry. Saturn, Uranus, Neptune. Each step outward adds years to transit times and vast quantities to fuel budgets. A Hohmann transfer to Neptune takes over 30 years. 30 years of coasting through the darkest, emptiest region of the solar system, where the Sun shrinks to a bright star and solar energy drops to a fraction of a percent of what Earth receives. This is where gravity assists become not merely helpful but essential. Without them, the outer solar system would be effectively unreachable with chemical propulsion. A gravity assist, and sometimes called a gravitational slingshot, uses a planet's gravitational field and orbital motion to change a spacecraft's velocity without burning any fuel at all. The spacecraft approaches a planet on a carefully calculated trajectory. It falls into the planet's gravity well, accelerating as it drops, curves around the planet, and departs in a different direction at a different speed. From the spacecraft's own perspective, its speed relative to the planet does not change. It enters the planet's gravitational sphere of influence at a certain relative velocity and leaves at the same relative velocity, just in a different direction. The planet's gravity does not add energy in the planet's reference frame. But from the Sun's perspective, something remarkable has happened. That the planet is itself moving along its orbit with a tremendous speed. Jupiter orbits the Sun at roughly 13 kilometers per second. When the spacecraft swings around Jupiter and departs in the same direction Jupiter is moving, it carries away some of Jupiter's orbital momentum. The spacecraft accelerates. Jupiter, in exchange, slows down by an infinitesimal amount, so small that it would take the mass of every spacecraft ever built, executing gravity assists for the remaining lifetime of the Sun, to change Jupiter's orbit by a single measurable degree. The trade is absurdly lopsided. The spacecraft gains enormous velocity. The planet loses nothing it will ever miss. Gravity assists are brilliant. They represent one of the most elegant solutions in all of mission design. Exploiting the geometry of orbital mechanics to obtain free velocity from planetary motion, they allow missions to the outer solar system that would be physically impossible with chemical rockets alone. The Voyager spacecraft used carefully planned flybys of Jupiter and Saturn to reach speeds exceeding 17 kilometers per second relative to the Sun, fast enough to escape the solar system entirely and drift into interstellar space. Without those gravity assists, the launch vehicle would have needed to provide all that velocity directly, requiring a rocket so enormous it could never have been built. The Cassini mission to Saturn used gravity assists from Venus twice, then Earth, then Jupiter, following a looping indirect path through the inner solar system before finally heading outward. And this baroque trajectory added years to the mission, but made it possible within the constraints of existing launch vehicles. New Horizons used a single Jupiter flyby to reach Pluto in about 9.5 years, instead of the decades a direct chemical trajectory would have required. And even that accelerated timeline meant the spacecraft arrived at Pluto moving too fast to stop. It flew past in a matter of hours, capturing images and data in a frantic burst before continuing into the Kuiper belt. But gravity assists are workarounds, not solutions. They depend on planetary alignments that occur infrequently. The alignment that allowed Voyager 2 to visit Jupiter, Saturn, Uranus, and Neptune in sequence occurs roughly once every 176 years. Voyager launched during a window that will not reopen until the 22nd century. Gravity assists also add years to mission duration, as spacecraft take indirect, spiraling routes through the solar system rather than direct paths, and they cannot be practically used for crewed missions to the outer planets, because the resulting transit times, often a decade or longer, even with optimal flybys, far exceed what human life support systems can sustain. The Oberth effect provides another clever exploitation of orbital physics, one that reveals just how deeply energy and velocity are intertwined. Named after Hermann Oberth, one of the founding pioneers of rocketry alongside Tsiolkovsky and Goddard, this effect demonstrates that a rocket burn produces more useful energy when performed at high velocity than at low velocity, and particularly when performed deep in a gravitational well, where the spacecraft is moving fastest. The physics behind the Oberth effect is straightforward once you see it. Kinetic energy is proportional to velocity squared. If you add a fixed amount of velocity to a fast-moving object, the increase in kinetic energy is larger than if you add the same velocity to a slow-moving object. A rocket burning 1 kilogram of fuel at 50 kilometers per second gains far more kinetic energy than the same rocket burning the same fuel at 5 kilometers per second, even though the velocity change from the burn is identical in both cases. This effect explains why mission planners sometimes design trajectories that dive deep into a gravitational well before performing major engine burns. The deeper you fall, the faster you move, and the more effective each unit of fuel becomes. The Parker Solar Probe exploits this principle on every orbit, swooping close to the Sun where its velocity reaches extraordinary values, using those close approaches to gradually reshape its orbit with maximum efficiency. Some proposed interstellar precursor missions envision a spacecraft diving extremely close to the Sun and then firing its engines at perihelion, the point of closest approach, to extract maximum energy from every kilogram of fuel. But the Oberth effect, like gravity assists, operates entirely within the constraints of the rocket equation. It improves the efficiency of fuel use in specific circumstances. It does not change the fundamental exponential relationship between desired velocity and required mass ratio. And it is a multiplier applied to the same underlying function, a way to get more value from each kilogram of propellant, but not a way to escape the exponential growth that makes high velocities so costly. It helps. It does not transform. What about alternatives to chemical propulsion entirely? If chemical energy is too weak, if the fine structure constant sets too low a ceiling on exhaust velocity, what happens when you turn to other energy sources? The most promising near-term option is nuclear thermal propulsion. Instead of burning chemicals to produce hot gas, a nuclear thermal rocket heats a working fluid, typically liquid hydrogen, by passing it through the core of a nuclear fission reactor. The reactor reaches temperatures far beyond what any chemical combustion can achieve, and the hydrogen, being the lightest element, achieves correspondingly higher exhaust velocities as it expands through the engine nozzle. Nuclear thermal engines achieve specific impulses of approximately 800 to 900 seconds, roughly double that of the best chemical engines. This improvement is genuinely significant. Doubling specific impulse does not merely halve the fuel requirement. Because of the exponential nature of the rocket equation, doubling exhaust velocity dramatically reduces the mass ratio needed for a given mission. A Mars transit requiring a mass ratio of 5 to 1 with chemical propulsion might require only about 2.5 to 1 with nuclear thermal engines. The savings compound across the entire mission architecture, reducing the total mass that must be launched from Earth, reducing the number of launches, reducing the cost, reducing the risk. NASA actually built and tested nuclear thermal engines during the 1960s under the NERVA program. The engines worked. They produced the expected thrust and specific impulse. They demonstrated that nuclear thermal propulsion is not speculative science, but proven engineering. The program was cancelled for budgetary and political reasons, not technical ones. Several current programs are working to revive the technology. But nuclear thermal propulsion does not break the exponential trap. It shifts the curve, making each step up the velocity ladder cheaper in fuel. But the ladder still grows exponentially. A nuclear thermal rocket capable of reaching Jupiter in reasonable timeframes still requires enormous propellant masses. And nuclear thermal technology introduces its own complications that do not exist for chemical systems. The reactor itself has substantial mass that must be accelerated along with everything else. Crew members need radiation shielding from the reactor during operation, adding more mass. Thermal management becomes critical, as reactor heat must be rejected into the vacuum of space through radiators. And the political and regulatory challenges of launching a nuclear reactor through Earth's atmosphere, with all the attendant risks of launch failure dispersing radioactive material, remain formidable. Ion drives represent a fundamentally different approach that trades thrust for efficiency in the most extreme way possible. Though these engines ionize a propellant, typically the heavy noble gas xenon, and accelerate the resulting ions using powerful electric fields. The ions exit the engine at velocities that dwarf anything chemical or nuclear thermal engines can achieve, reaching 30 to 50 kilometers per second or more. Specific impulses range from 1500 to over 3000 seconds, 5 to 10 times higher than the best chemical engines. By the metrics of the rocket equation alone, ion drives are vastly superior. The exponential penalty for any given velocity change shrinks dramatically when exhaust velocity increases by a factor of 10. Missions that would require absurd mass ratios with chemical propulsion become feasible with ion drives. The catch is thrust. Ion drives produce incredibly small forces, and a typical ion engine generates thrust measured in millinewtons, roughly the force exerted by a single sheet of paper resting on your outstretched palm. A chemical rocket engine produces millions of newtons. The difference spans 9 or 10 orders of magnitude. This means ion drives cannot launch from planetary surfaces. They cannot fight gravity. They cannot accelerate quickly. They are useful only in the vacuum of space spun from any significant gravitational well, where their gentle but continuous acceleration can build up large velocity changes over weeks and months and years of patient, unrelenting thrust. The Dawn spacecraft demonstrated ion propulsion's potential beautifully. Using 3 xenon-ion engines, Dawn visited the asteroid Vesta and then travelled onward to the dwarf planet Ceres, achieving total velocity changes exceeding 10 km per second, far more than any chemical system could have provided given Dawn's launch mass. But the journey took years. Dawn launched in 2007 and did not arrive at Ceres until 2015. 8 years of spiralling slowly outward, gradually reshaping its orbit, accumulating velocity a few millimeters per second at a time. For robotic missions, this patience is acceptable. Robots do not eat, they do not breathe, they do not develop bone density loss, or suffer psychological deterioration from years of confinement. For crewed missions, the trade-off becomes deeply problematic. Humans need life support systems that consume mass and power continuously. A mission that takes years instead of months requires proportionally more food, more water, more oxygen, and more spare parts. and more radiation shielding to protect biological tissue from the relentless bombardment of galactic cosmic rays. The mass saved by efficient propulsion may be entirely consumed and then exceeded by the mass of extended life support. Ion drives solve the fuel problem by creating a consumables problem. The exponential trap is not defeated. It simply migrates from one column of the mass budget to another. Solar sails offer what appears to be the ultimate escape from the exponential trap. These enormous reflective surfaces use the pressure of sunlight itself to generate thrust. Photons carry momentum despite having no mass. When they strike a reflective surface, they transfer that momentum, pushing the sail in the direction away from the sun. No fuel is required, no propellant is consumed. The spacecraft can accelerate continuously as long as sunlight falls on the sail, and sunlight in the inner solar system never stops. In principle, solar sails eliminate the rocket equation entirely. No fuel means no exponential penalty. No propellant mass means no compounding. The spacecraft's mass stays constant throughout the mission. It is, on paper, the perfect propulsion system. But solar radiation pressure is extraordinarily weak. At Earth's distance from the Sun, sunlight exerts a pressure of roughly 9 micronewtons per square meter. 9 micronewtons. To put this in perspective, the gravitational force on a single raisin sitting on a kitchen table is roughly 10,000 times stronger than the solar radiation pressure on a square meter of perfect reflector in space. And accelerating even a modest payload to useful velocities requires sails measuring hundreds of meters or even kilometers across. The structural challenges of deploying and maintaining such enormous gossamer structures in space, structures that must remain perfectly flat and reflective while being thinner than plastic wrap, are immense and largely unsolved. And solar pressure diminishes with the square of distance from the Sun. At Jupiter's orbit, solar pressure is roughly 4% of its value at Earth. At Saturn, roughly 1%. Solar sails become progressively more feeble as they move outward through the solar system, losing effectiveness in precisely the region where alternative propulsion is most desperately needed. And every alternative propulsion concept faces its own version of the constraints Feynman would have identified instantly. Chemical rockets have high thrust but limited exhaust velocity, trapped beneath the ceiling of electromagnetic bond energies. Nuclear thermal engines improve exhaust velocity meaningfully but add reactor mass and regulatory complications. Ion drives achieve excellent exhaust velocity but produce thrust so negligible that missions stretch across years. Solar sails eliminate fuel entirely but generate forces so small they require structures of absurd scale and become useless in the outer solar system. Each technology represents a different compromise within the same physical framework. Each trades one constraint for another. None escapes them all. Now extend the problem beyond the solar system entirely, and watch the mathematics become truly terrifying. The nearest star system, Alpha Centauri, lies approximately 4.4 light-years from Earth. A light-year is the distance light travels in 1 year, approximately 6 trillion miles. Alpha Centauri is roughly 25 trillion miles away. At the speed of the Voyager 1 probe, currently the fastest human-made object relative to the Sun at roughly 17 kilometers per second, reaching Alpha Centauri would take approximately 73,000 years. 73,000 years. Human civilization in its entirety, from the first agricultural settlements to the present day, spans roughly 10,000 years. The journey to the nearest star at our best current speed would take 7 times longer than the entire history of civilization. So to make the trip in a single human lifetime, say 50 years, a spacecraft would need to travel at roughly 10% of the speed of light, approximately 30,000 kilometers per second. This is not a casually large number. It is a velocity so extreme that it redefines what energy means. The kinetic energy of a 1,000 kilogram payload moving at 10% of light speed is approximately 450 trillion joules. That is roughly the total energy output of a large nuclear power plant running at full capacity for 5 continuous years, concentrated in a single small spacecraft weighing about as much as a compact car. The energy is real. The physics is not negotiable. Accelerating 1 metric ton to 10% of light speed requires that much energy, regardless of how you deliver it. The no cleverness in propulsion design changes the kinetic energy equation. It is a fundamental relationship between mass and velocity that sits beneath all engineering. Achieving this velocity with any reaction drive, any system that operates by expelling mass, requires fuel quantities that make the Saturn V look like a firecracker. The rocket equation applies to interstellar travel with the same exponential cruelty it applies to orbital launches, but at velocity scales that amplify the exponential factor enormously. Even with the most optimistic nuclear fusion propulsion, a technology that does not yet exist in any practical form, and where exhaust velocities might theoretically reach 5 to 10% of light speed, the mass ratio for accelerating to 10% of light speed and then decelerating at the destination to actually stop and explore, rather than flash past in a matter of hours, would be daunting. The total mass ratio for a round trip, accelerating, decelerating, accelerating again for the return, and decelerating once more at Earth, climbs into the territory where the fuel mass dwarfs the payload mass by factors of hundreds or thousands. And fusion propulsion does not exist yet, not as a rocket engine, not even as a reliable power source on Earth. After 70 years of research and tens of billions of dollars of investment, no laboratory on the planet has achieved sustained net positive energy production from controlled nuclear fusion. Building a compact, lightweight, reliable fusion engine capable of operating continuously in the vacuum of space for decades while producing thrust sufficient to accelerate a crewed vehicle to a significant fraction of light speed represents not one engineering challenge, but dozens stacked atop each other, each dependent on solving the one below. The exponential trap applies to interstellar travel with brutal terminal finality. Each additional percentage point of light speed demands exponentially more fuel. The distances are so vast and the velocities so extreme that the rocket equation crushes every conventional propulsion concept beneath its exponential weight. The curve does not merely steepen, it goes nearly vertical. The fuel requirements do not merely grow large, they grow absurd, then they grow impossible. And then they keep growing. Feynman would have found this conclusion unsettling but fundamentally honest. It is the kind of truth he built his career on. Truths that do not flatter human ambition but respect physical reality. Nature does not owe us convenient physics. The universe was not designed for easy traversal, it was not designed at all. The same laws that allow stars to shine and galaxies to form and atoms to bond into molecules capable of contemplating their own existence also impose taxes on motion that grow without limit as ambitions increase. The laws are neutral. They do not care whether the traveller is a robotic probe or a crude starship carrying the hopes of a civilization. The exponential function treats all payloads with the same mathematical indifference, though the dream of interstellar travel is not impossible in any absolute physical sense. The laws of physics do not forbid a spacecraft from travelling at 10% of light speed. No conservation law is violated, no relativistic barrier is breached. But the laws of physics make it so extraordinarily expensive in energy terms that achieving it would require capabilities so far beyond anything humanity currently possesses that the gap cannot be honestly described as an engineering challenge. It is a gap of fundamental energy access, a chasm between the energy scales available to our civilization and the energy scales required by the distances involved. This is the desert beyond Earth's gravity well, not empty in the sense of being barren or featureless. The solar system contains dozens of fascinating worlds, hundreds of moons, and millions of asteroids, and scientific questions that would keep 1,000 civilizations busy for millennia, but empty in the sense of offering no assistance, no shortcuts, no free energy, and no mercy for insufficient preparation. Every meter per second of velocity must be paid for, and the currency exchanges at an exponential rate that nature itself established when the universe fixed its constants, and cannot be persuaded, petitioned, or negotiated into changing. The question that remains is what all of this means, not just for engineering or mission planning or national space budgets, but for how we understand ourselves and our place in a universe whose rules we can read but cannot rewrite. Richard Feynman stood in front of a lecture hall at Caltech in the early 1960s, chalk dust on his fingers and a half-finished diagram on the blackboard behind him, and said something that has stayed with physicists for more than 6 decades. He told his students that the thing that does not fit is the thing that is most interesting. Not the measurement that confirms the theory, not the result that matches the prediction, the anomaly, the surprise, the constraint you did not expect. That is where the deepest truths live. He did not mean that physics should bend to human wishes. He did not mean that the rules of nature are negotiable if you're clever enough or persistent enough or well-funded enough. He meant the opposite. He meant that the constraints nature imposes, the walls it builds around what is possible, are not obstacles to understanding, but the very substance of understanding. Find the constraint, and understand why it exists, accept it, and then within the space it allows, do everything you can. This philosophy runs through everything Feynman ever worked on. He did not complain that quantum mechanics was counterintuitive. The particles seemed to travel every possible path simultaneously. That observation changed the outcome of experiments. That certainty was replaced by probability at the most fundamental level. He embraced its strangeness and found beauty in the astonishing precision of its predictions. Predictions that matched experimental results to more than 10 decimal places. The most accurate agreement between theory and measurement in the history of science. He did not protest that the weak nuclear force violated parity symmetry, a discovery that overturned a principle physicists had assumed was sacred, that he helped develop the theoretical framework that explained why parity was violated and what that violation revealed about the deep structure of matter. Feynman's genius was not in wishing nature were different. It was in understanding nature as it actually is, and finding wonder, genuine unforced wonder, in the understanding itself. He once described the pleasure of finding things out as one of the great experiences available to a human being. Not the pleasure of being right, not the pleasure of winning an argument, the pleasure of seeing how something works and recognizing in that mechanism a beauty that is available only to those who take the time to look closely. When we apply this philosophy to the problem of space travel, to the 3 layers of constraint we have explored across these hours, the conclusions are both sobering and strangely unexpectedly liberating. The exponential trap is real. The gravity tax is real. The desert that stretches between worlds is real. The tyranny of the rocket equation is not a temporary inconvenience awaiting a clever solution in some future laboratory. It is a permanent feature of the universe, rooted in Newton's third law, in the conservation of momentum, in the energy density of chemical bonds determined by the fine structure constant, in the depth of planetary gravity wells carved by masses that coalesced billions of years before any creature evolved to resent them. These are not bugs in the cosmic software. They are the software. They are the rules the universe runs on, as fundamental as the speed of light and the charge of the electron. They were established when the cosmos was born, and they will persist until it dies. Feynman would not have despaired at this realization. Despair was not in his character, and more importantly, it would have been the wrong response. Despair assumes that a constraint is a punishment, something inflicted on you that should not be there. Feynman saw constraints differently. He saw them as information, as structure, as the shape of reality revealing itself to anyone honest enough to look. He would have asked the next question, the question he always asked when a constraint became clear. Given these rules, what can we actually do? The answer, it turns out, is more than you might expect. As long as you respect the physics. Low Earth orbit is accessible. The gravity tax is severe, but chemical rockets can pay it. Almost 70 years of spaceflight has demonstrated beyond any reasonable doubt that reaching orbit is expensive but achievable. The International Space Station has been continuously occupied for a quarter century. Rotating crews of astronauts and cosmonauts living and working in microgravity for months at a time. Conducting research in material science, biology, medicine, and fundamental physics. Thousands of satellites orbit Earth right now, providing global communications, weather monitoring, navigation accurate to within a few meters, agricultural surveillance, climate observation, and scientific measurements that would be impossible from the ground. Space tourism, which was dismissed as fantasy 20 years ago, is now a functioning commercial industry. Private citizens have flown to orbit. Others have reached suborbital space on vehicles designed specifically for paying passengers. The orbital domain is open. It is constrained by economics, by the cost of paying the gravity tax and the exponential fuel penalty for every kilogram lifted above the atmosphere. But it is not forbidden by physics. The boundary between Earth and space has been crossed thousands of times. It will be crossed thousands more. This is not aspiration. This is accomplished fact. The moon is accessible. Apollo proved this more than half a century ago, when 12 human beings walked on the lunar surface and returned safely. Each mission carrying them across roughly 500,000 miles of vacuum and back, using technology that is by modern standards astonishingly primitive. The computers that guided the Apollo spacecraft had less processing power than a modern digital wristwatch. The navigation was partly manual, performed by astronauts taking star sightings through a telescope and entering corrections by hand. The life support systems were robust but simple, and yet it worked 6 times. The velocity budget for a lunar mission is large but sits well within the capability of chemical propulsion. Modern mission architectures using reusable launch vehicles and in-orbit refueling could make regular lunar access far more affordable than Apollo ever was. Lunar bases are physically feasible with current technology. The structures, the life support, the power generation, the radiation shielding. All of these present engineering challenges, some of them formidable, but none that violate known physics. And because the Moon's gravity well is so much shallower than Earth's, once infrastructure exists on the lunar surface, it becomes a natural staging point for deeper missions, a logistics hub from which spacecraft depart at a fraction of the energy cost of climbing out of Earth's atmosphere. Mars is at the ragged edge of what chemical propulsion can support for crewed missions, and the raggedness of that edge is part of what makes it so fascinating. The transit times are long, the round trip measured in years rather than weeks. The logistics of keeping human beings alive and functional throughout are formidable, but the physics does not forbid it. Nothing about a crewed Mars mission violates any known law of nature. The engineering challenges are immense but conceivable, meaning that people who understand the relevant disciplines can describe what needs to be built and how it would work, even if building it will take decades of effort and billions of dollars. Manufacturing return fuel from the Martian atmosphere rather than carrying every gram from Earth could reduce the launch mass substantially. The chemistry involved is well understood. Scaling it to another planet is an engineering challenge, not a physics problem. A Mars colony, a permanent human presence on another world. It sits within the realm of physical possibility. It is not yet within the realm of economic or political reality. But the physics says yes. That matters more than most people appreciate. Beyond Mars, the constraints tighten dramatically. And here, Feynman's insistence on honesty becomes especially important. Though crewed missions to the outer solar system would require propulsion technologies that do not yet exist in practical form. Nuclear electric propulsion could in principle shorten transit times to Jupiter's moons from decades to years. But the engineering challenges of operating reactors autonomously in space, shielding crews and managing waste heat in a vacuum remain severe. These problems are not insoluble, but they are unsolved, and there is an important difference between those two words that Feynman would have insisted we respect. Robotic exploration of the outer solar system will continue to yield extraordinary science. It already has. The Voyager missions transformed our understanding of Jupiter, Saturn, and their moons. Cassini spent 13 years orbiting Saturn, her revealing the intricate structure of its rings and discovering geysers on the moon, Enceladus that spray water ice into space from a subsurface ocean. The Juno mission is currently studying Jupiter's atmosphere and magnetic field in unprecedented detail. Europa Clipper will investigate the potential habitability of Jupiter's ice-covered moon, Europa, probing the ocean that lies beneath miles of frozen crust. Future missions might explore Titan's methane lakes, the only bodies of stable liquid on any surface other than Earth's in the solar system. They might sample the plumes of Enceladus directly, searching for organic molecules that would hint at biological activity in its hidden ocean. They might map the magnetic fields of the ice giants, Uranus and Neptune, planets so poorly understood that we have only a single flyby of each. To Voyager 2's brief encounters in 1986 and 1989, these missions are possible because robots tolerate constraints that humans cannot. Robots do not eat, they do not breathe, they do not need exercise equipment to prevent bone loss. They do not suffer from loneliness, boredom, or the psychological strain of years-long confinement in a metal tube millions of miles from the nearest other human being. They do not require return trips. They can be designed for the specific constraints of each destination. Optimized for the exact radiation environment, temperature range, and communication delay they will face. The exponential trap is less punishing when the payload does not need to be kept alive. Feynman's way of thinking leads to an important distinction that popular culture and sometimes even the space industry itself tends to blur in the excitement of its own ambitions. There is a difference between difficult and impossible. The rocket equation makes space travel difficult. It does not make it impossible. But the degree of difficulty varies so enormously depending on the destination that collapsing all space travel into a single category of hard but doable is not just imprecise, it is misleading. Reaching low Earth orbit is difficult. Reaching the moon is very difficult. Reaching Mars is extraordinarily difficult. Reaching the outer planets with human crews is currently beyond practical capability, though not beyond the laws of physics. Reaching another star system is so far beyond current capability that it belongs in a different category entirely, one where the gap between aspiration and available physics spans not years of engineering development but orders of magnitude in energy access. This hierarchy is not a ladder that technology steadily climbs, each rung a predictable step above the last. Each transition upward requires not just incremental improvement, but a fundamental change in energy source. And each such change carries its own constellation of scientific, engineering, political, and safety challenges. The jump from chemical rockets to nuclear propulsion is not like the jump from propeller aircraft to jets. It is a leap to an entirely different domain of physics. And the jump from any propulsion technology we currently possess to anything capable of reaching another star within a human lifetime likely requires physics we have not yet discovered. This is not pessimism. It is an honest assessment of where the boundaries of known physics lie relative to the energy requirements of interstellar travel. Feynman would have insisted on this honesty with the particular intensity he reserved for self-deception, which he considered the most dangerous kind of dishonesty, because it is the hardest to detect. His entire career was built on the principle that the person you are most likely to mislead is yourself, and that guarding against that tendency is the single most important discipline in science. When optimistic futurists promise interstellar travel within a century, when entrepreneurs suggest that colonizing Mars is merely a matter of willpower and funding, when science fiction conflates the genuine difficulty of reaching orbit with the fundamentally different difficulty of reaching another star, Feynman's intellectual framework demands that we ask uncomfortable questions. What is the energy source? What is the mass ratio? What does the rocket equation say? If the answers involve technologies that do not exist, physics that has not been discovered, and energy scales that exceed current civilization's total output, then the promise is aspiration, not prediction. Aspiration has value, but confusing it with prediction is exactly the kind of self-deception Feynman spent his life warning against. This does not mean we should stop dreaming. Feynman himself was one of the most imaginative, playful, restlessly curious scientists who ever lived. He played bongo drums at parties and in faculty meetings. He painted portraits of his friends under a pseudonym. He cracked safes at Los Alamos during the Manhattan Project for the sheer intellectual pleasure of figuring out the mechanisms. He learned to draw, learned to speak Portuguese well enough to lecture in Brazil, studied Mayan mathematics, became fascinated by ants in his kitchen, and once spent an evening trying to understand why spaghetti breaks into 3 pieces instead of 2 when you bend it. His curiosity had no boundaries and no pretensions. He was as delighted by a simple puzzle as by a profound one. But his imagination was disciplined by physics, and he dreamed within the constraints nature provided and found that the constrained space was rich enough to fill a lifetime with wonder. He did not need the laws of physics to be different in order to find them fascinating. He found them fascinating because of what they were, not despite it. The same applies to humanity's relationship with space. The constrained space available to us is genuinely breathtakingly rich. Within the solar system, there are dozens of worlds worth exploring, each one a laboratory of geology, chemistry, and atmospheric science, unlike anything else. Hundreds of moons orbit the outer planets, some with subsurface oceans, some with active volcanoes, some with atmospheres denser than Earth's. Millions of asteroids and comets carry material preserved from the formation of the solar system 4.5 billion years ago. Cosmic time capsules containing clues about how planets form and how the ingredients of life get distributed across stellar systems. The resources available within the solar system could sustain human civilization for millions of years without requiring any breakthrough in fundamental physics. The asteroid belt contains more accessible mineral wealth than the entire crust of Earth. Individual metallic asteroids harboring quantities of platinum, nickel, and iron that dwarf terrestrial reserves. The water ice confirmed on the Moon's poles and buried beneath the surface of Mars could support permanent settlements with drinking water, breathable oxygen, and rocket fuel, all derived from local resources. The energy of the Sun, captured by the space-based solar collectors operating in continuous sunlight unfiltered by atmosphere, dwarfs any terrestrial energy source by factors so large they are difficult to comprehend. A single square kilometre of solar collectors in orbit around Mercury would generate more electrical power than a large nuclear power plant on Earth. All of this is accessible within the constraints of known physics. None of it is easy. All of it requires respecting the exponential trap rather than ignoring it, designing around the rocket equation rather than pretending it does not apply, working within the gravity tax rather than wishing it were lower. The organizations and individuals who succeed in space over the coming decades and centuries will be those who understand the physics most deeply and find the cleverest, or most honest paths through its constraints. Not the ones who make the boldest promises, but the ones who do the hardest math. There is a philosophical weight to all of this that extends far beyond engineering, far beyond budget discussions and launch manifests and mission timelines. It touches something fundamental about the human condition that Feynman, for all his focus on physics, would have appreciated. Human beings evolved on a planet whose gravity well is deep enough to trap us, but whose atmosphere is transparent enough to show us the universe. We can see what we cannot easily reach. Every clear night, the sky presents destinations that would take millennia to visit, stars that will burn out before any spacecraft we could build would arrive at their doorstep. But we can observe galaxies so distant that the light reaching our telescopes began its journey before the Earth existed. Yet we cannot send even a grain of sand to the nearest of those galaxies within any time frame meaningful to human civilization. This is a unique existential position in the history of life on this planet, and possibly in the history of life in this galaxy. No other species on Earth contemplates the stars with the understanding that reaching them is physically possible but practically prohibitive. No other creature calculates the energy budget of an interplanetary transfer orbit and then stares at the result in silence. We are, as far as we know, the only beings in this corner of the cosmos who can see the prison walls, understand the physics that built them, calculate their exact height, and feel the peculiar ache of knowing what lies beyond them. Feynman found liberation in exactly this kind of understanding. He believed and demonstrated throughout his life that knowing why something is difficult, truly grasping the physics behind the constraint, transforms frustration into something good. Not resignation, not surrender, something closer to respect. You stop blaming engineers for not trying hard enough. You stop believing that the right amount of funding or the right political will would dissolve the problem. You start marveling at how much has already been achieved within limits set not by human inadequacy, but by the architecture of the universe itself. Every rocket that reaches orbit is a triumph over exponential mathematics. Think about what that means. Yet a group of human beings standing at the bottom of a deep gravitational well on a planet wrapped in a thick atmosphere figured out how to assemble volatile chemicals in a controlled configuration, ignite them, direct the resulting explosion downward with enough precision to lift a payload through the atmosphere, and accelerate it to 17,500 miles per hour without destroying it into the process. They did this while fighting gravity, drag, heating, vibration, and the compounding exponential penalty that demands 95% of the vehicle be sacrificed as fuel. And it works, not every time, but often enough to be routine. That is not a failure. That is an astonishing success achieved in the teeth of constraints that most people never bother to understand. That every probe that reaches another planet is a testament to human cleverness operating at the exact boundary of what physics permits. The Voyager probes carry scientific instruments built in the 1970s that are still returning data from interstellar space after nearly half a century of continuous operation. The Mars rovers have driven miles across alien terrain, conducting geology experiments that would have required a human field team on Earth, but performed autonomously by machines controlled from hundreds of millions of miles away, with communication delays measured in minutes. These achievements do not happen despite the exponential trap. They happen through intimate understanding of it. Every astronaut who has ever floated in microgravity and looked down at the curved blue horizon of Earth has paid a gravitational toll measured in millions of joules per kilogram, a toll extracted from thousands of tons of fuel burned in minutes. And every single one of them has reported that the view from the window, the thin blue line of atmosphere, the blackness beyond, the fragile beauty of the only home our species has ever known, was worth every joule and every dollar. Could new physics someday change the equation? Could some discovery lurking in the gaps of our current understanding offer a path around the exponential trap rather than through it? Possibly. Intellectual honesty requires admitting the possibility, just as it requires refusing to count on it. Our understanding of the universe is demonstrably incomplete. The dark energy accelerates the expansion of the cosmos through mechanisms we do not understand. Dark matter makes up roughly 27% of the universe's total energy content, and but refuses to interact with light or any detector we have ever built. Quantum mechanics and general relativity, the two most successful and most rigorously tested theories in the history of physics, flatly contradict each other at extreme scales, producing nonsensical infinities when you try to apply both simultaneously. Somewhere in the resolution of these contradictions, somewhere in the physics that unifies gravity with quantum mechanics, there might be principles that enable propulsion methods we cannot currently imagine. But intellectual honesty also demands we acknowledge that the word might is doing an enormous amount of work in that sentence. As every propulsion breakthrough in the history of spaceflight has operated within physics that was already known at the time the technology was conceived. Chemical rockets exploit thermodynamics and Newtonian mechanics, both well established before the first rocket flew. Ion drives exploit electrodynamics understood since Maxwell. Solar sails exploit radiation pressure predicted by Maxwell's equations and confirmed experimentally in the early 20th century. Nuclear propulsion exploits the strong nuclear force understood since the 1930s. Each of these technologies was predicted by existing theory before it was built. No propulsion system in history has ever emerged from physics that was genuinely unknown at the time of its conception. Every one was an application of principles that were already sitting in textbooks, but waiting for engineers brave enough to build hardware around them. This does not preclude future surprises. The history of science is punctuated by discoveries that opened entirely new technological domains that no one anticipated because no one knew the underlying physics existed. Electromagnetism enabled everything from telegraphs to computers to magnetic resonance imaging, none of which could have been predicted before Faraday and Maxwell. Nuclear physics enabled both weapons of terrifying power and power plants that generate electricity for hundreds of millions of people. Quantum mechanics enabled semiconductors, lasers, atomic clocks, and the entire digital infrastructure of modern civilization. And a comparable breakthrough in fundamental physics could in principle transform our propulsion capabilities in ways that are currently unimaginable. But Feynman would have counseled patience and skepticism in equal measure. The same patience and skepticism he applied to every claim that crossed his desk. He knew that nature reveals its secrets slowly, on its own schedule, indifferent to human impatience. He knew that wishful thinking is the enemy of scientific progress, that wanting something to be true is the fastest way to stop yourself from discovering whether it actually is true. He would have said what he always said: study the physics, follow the evidence, test every claim against reality, and do not confuse what you hope to find with what you actually find. In the meantime, the universe remains what it is, and a place of staggering beauty, incomprehensible scale, and unforgiving physical constraints. A cosmos that operates according to rules it did not choose and cannot change. Rules that permit stars to burn and galaxies to spin, and atoms to bond into molecules complex enough to wonder about their own existence. But that also imposed taxes on motion that grow exponentially with ambition and offer no discounts for good intentions. We are a species that emerged on a wet rock, orbiting a medium-sized star in the outer suburbs of an ordinary spiral galaxy. We figured out how to leave our planet using controlled explosions of refined chemicals, strapping ourselves to towers of kerosene and liquid oxygen and riding columns of fire through the atmosphere. We walked on the moon, we sent robots to Mars, but we launched probes beyond the heliosphere into interstellar space where they still whisper faintly back to us across billions of miles of emptiness. Every one of those achievements was accomplished in the teeth of the exponential trap. Every one required accepting the physics rather than fighting it, finding paths through the constraints rather than wishing them away, paying the full gravitational toll without complaint, and making the most of whatever remained after the equations took their share. That is Feynman's legacy applied to space. Not the specific equations he wrote, not the specific lectures he delivered in that chalk-dusted classroom at Caltech, though those lectures remain among the finest ever given. His legacy is the way of thinking he embodied and tried to teach. Start from first principles, then identify the real constraints, the physical ones, not the political or emotional or institutional ones. Understand why those constraints exist. Accept them without resentment. Do not fool yourself about what is possible and what is not, because you are the easiest person to fool. And then within the space the constraints allow, within the narrow band of possibility that nature permits, build something beautiful. The rocket equation is not our enemy. It is our teacher. It tells us with perfect honesty and zero sentimentality exactly how hard each step will be, what it will cost in fuel and mass and energy, what we must bring along to have any chance of arriving. It does not exaggerate, it does not minimize, it does not lie. And it is honest in a way that optimistic projections and science fiction narratives and political speeches about the future of space rarely are. And honesty, as Feynman spent his entire extraordinary life demonstrating, is the foundation on which all real progress is built. Not optimism, not ambition, not funding. Honesty. Space is hard because physics says it must be. The exponential penalty on moving mass through a vacuum is not a problem to be solved. It is a fact to be understood, respected, and worked within. The universe does not owe us easy travel between its wonders. It does not owe us interstellar highways or warp drives or physics that bends to match our science fiction. It owes us nothing. It gave us the laws, and the laws are the laws, and they apply equally to every kilogram of mass in every corner of the cosmos. Earth that we travel at all, carrying fuel that carries fuel that carries fuel, each kilogram fighting the exponential curve that nature set before any star was born, before any planet cooled, before any molecule assembled itself into a living cell, capable of wondering whether there might be other living cells elsewhere. That is the remarkable part. Not that space is difficult. It was always going to be difficult. The constants were set at the beginning. The equations were written into the structure of reality. The exponential trap was waiting for us before we existed. The remarkable part is that we go anyway. Feynman once looked at a simple flower and saw not just beauty, but the intricate physics that made the beauty possible. The cellular machinery that built the petals from sunlight and carbon dioxide. The quantum chemistry that determined the pigments, the evolutionary pressures that shape the colour and the scent to attract specific pollinators, the fluid dynamics of water moving through the stem. He said that understanding the science behind the flower did not diminish its beauty. It added to it. It added layers of beauty, invisible to anyone who merely looked at the surface. The same is true of space travel. Understanding why it is hard. Truly understanding the exponential trap and the gravity tax and the desert of distance that stretches between the worlds. It does not diminish the achievement of those who travel it. It magnifies it. Every launch becomes more impressive when you know the physics working against it. And every mission becomes more heroic when you understand the exponential penalty being paid in full with every kilogram. Every image returned from another world becomes more precious when you grasp how much energy, ingenuity, and sheer stubbornness was required to place the camera that took it. We live at the bottom of a deep gravity well on a planet wrapped in a thick atmosphere, orbiting a star that is one of 400 billion in a galaxy that is one of 2 trillion in the observable universe. We can see almost all of it. We can reach almost none of it. The gap between what we can observe and what we can visit is not a temporary limitation of current technology. It is a permanent feature of existence in a universe governed by the speed of light and the rocket equation. And yet we keep building rockets, keep designing missions, and keep calculating trajectories, keep sending pieces of ourselves, our instruments, our curiosity, our stubborn refusal to accept that the prison walls are the end of the story, outward into the cosmos. Feynman would have loved that, not because it is easy, but precisely because it is not.